Welcome back to Statistics, everyone. It's Thursday, April 2nd, and today we're going to talk a little bit more about confidence intervals and significance tests, and particularly the relationship between those two. There's a nice way to think about the relationship that actually adds insight to what both confidence intervals and significance tests are telling us. And so that will be we'll be going through that in just a second. But before we do, let me just reiterate to you that I know this is unusual for everybody and difficult, this online situation we find ourselves in. I think to keep engaged is really the main thing. So stay tuned to your Hamden Sydney email for messages about more videos and homework assignments, and please feel free to let me know if you're going through some kind of issue or difficulty that uh, is preventing you from doing homework or interfering with your ability to get it, or whatever. We can arrange some sort of a video conference or something like that. And of course, you can always just ask questions by email as well. But I'm here to help, and so keep that in mind, and just stay engaged. Keep on plugging. We'll get through this together. Yeah. So let's think about the last few concepts we've covered and see if we can find a relationship between them. Confidence intervals on the one hand, which are about estimating a parameter, and significance tests on the other, which talk about making claims about a parameter. Uh, so I want to sort of put this discussion in the context of an example. An SRS of 100 seventh graders from a large school district were tested, and the average IQ in the sample was 103.7, so slightly above average. Assuming IQ is normally distributed with a standard deviation of sigma equal 15, what can we say about the true mean IQ among all seventh graders in this district? So the two main mechanisms we have for saying something about a population mean given sample data are confidence intervals and significance tests. A confidence interval estimates the true mean with a confidence interval, and a significance test evaluates evidence for and against claims about uh, a population mean mu. So in this situation, let's start by looking at both of those things and asking ourselves, what do they tell us and how do they relate? So let's start with a confidence interval. Confidence intervals are nice because they're pretty easy to compute once you figure out the basic recipe. You need the standard deviation of the sample statistic, so that's the population standard deviation divided by the square root of the sample size. In our case, that turns out to be 1.5. The critical value for the confidence interval, z star, is the upper bound of the middle, whatever percent your confidence level is of the standard normal distribution. So the middle 95%, the upper bound of that would have be the 97.5th percentile. So we have this inverse norm calculation that gets us 1.96. Uh, a little note here too. You may remember that when we started talking about confidence intervals, we said, well, for 95% confidence, you need two standard deviations of x bar. And here, this calculation says 1.96. Why the difference? Well, the only thing that's going on there is that the two standard deviations for 95% confidence is kind of a rule of thumb from the 68, 95, 99.7 rule. The 1.96 that you get by just following the recipe for confidence intervals is the slightly more accurate figure, 1.96. Of course, that's very close to 2, but we'll go with the more accurate figure here. Then the margin of error is the critical value times the standard deviation of x bar. Turns out to be 2.94. And so our 95% confidence interval would be our mean x bar plus or minus that margin of error. So that turns out to be from 100.76 to 106.64. So we're 95% confident that the true mean average IQ among all seventh graders in the school district was between this 100.76 and 106.64. Let's look at a two-sided significance test for that same mean mu. So, and I'm going to do something a little kind of new here. The null hypothesis I'm going to leave as mu equals mu naught. Mu naught would just be whatever value you happen to find in the null hypothesis. And it's sometimes called the null value, mu naught. So, and then the alternative we're going to consider is a two-sided alternative, mu not equal to mu naught. So this mu naught would be the same in the null and alternative hypotheses. So, for instance, if the mu naught were 100, would be testing the null hypothesis that the average was 100 versus the alternative hypothesis that the true average was different than 100. So, in other words, the null hypothesis, if mu 0 were 100, would be, in words, the seventh graders in this school district on average have an IQ of 100. In other words, they have the average IQ. If mu 0 were 105, we would be testing the null hypothesis that the mean is 105 versus the alternative that it's not 105. And the null hypothesis in this case would be simply claiming that seventh graders are somewhat above average, right, with an average IQ of 105. And if you were testing mu equal 120 versus mu not equal 120, you'd essentially, the null hypothesis would be saying that the seventh graders are, pretty far above average in this school district. So I want to leave that that value in the null hypothesis as kind of a variable right now, because I want to ask the question, what values of that null hypothesis, that mu 0, what values would cause us to reject the null hypothesis at the alpha equal 5% significance level? So we want to figure out, if we can, what values would we reject and what values would we fail to reject in this null hypothesis if we did a significance test. So the way to look at that is to look at to carry out the significance test, at least as far as we can, using mu 0 as our null value. So the test statistic is just going to be, as usual, the z-score for x bar minus the value in the null hypothesis over the standard deviation of x bar. So I'm just plugging in what we know there, and you see it's 103.7 minus the mu 0, which comes from the null hypothesis, over 1.5. And then when would this test statistic cause the p-value to drop below 5%, right? Because that's when we reject the null hypothesis. When the p-value is less than your alpha value, then you're going to reject the null hypothesis. So we need to ask, when would this test statistic cause us to have a p-value that's below 5%? So let's work our way through this. The idea I want to use is, let's first find the test statistic that would result in a p-value of exactly 5%. And this is just going to be kind of a benchmark so that we can then answer the question, well, when would the p-value be less than 5% so that we reject the null? So when we ask this question, when is the p-value exactly going to be 5%, that brings in the standard normal distribution. Why? Because the p-value is about z-scores, and z-scores have a standard normal distribution. Now, we're doing a two-sided significance test here. So there's actually going to be two z-scores, two test statistics that give us a 5% p-value. And that's because in a two-tailed test, you look at both the tail to the right of 0 and the tail to the left of 0. Now, to have a p-value of 5%, you look at all z-scores that are at least as extreme as the ones you got. And remember, my z-star and negative z-star means, whatever z-score we needed to get that 5% significant, 5% p-value. So our p-value would be the probability in both tails to the left of negative z-star and the right of positive z-star. That would be our p-value, that green shaded region there. Because we want the p-value to be 5%, the total area in both tails would need to be 5%. And so each tail itself would have to have 2.5%. And that means that in the middle, we would have 95%, right? Because the total area has to add up to 100%. And so the p-value then, the z-score we need for the 5% p-value would be just the inverse norm of 0.975. I remember I'm looking at z-star here for the moment, and the percentile of z-star is the 95% plus the 2.5% or the 97.5th percentile. So we have inverse norm of 0.975, and that turns out to be 1.96. And of course, the negative of that would also give us that same 5% p-value, because again, if my test statistic were negative 1.96, the p-value, because it's a two-sided test, would still be both tails. So you'd still get that p-value of 5%. So a test statistic of 1.96, let me go back. A test statistic of either 1.96 or minus 1.96 would give me a p-value of exactly 5%. So when would the p-value be less than 5%? Well, it would be either if your actual test statistic were greater than 1.96%, right? So I'm showing here's a test statistic like that. It's greater than 1.96. The p-value associated with that test statistic would again be both tails, the one to the right of z and the one to the left of negative z. And you can tell that that red area is going to be less than 5% because it's contained in the green area, which we know is 5%. So a test statistic bigger than 1.96 would give us a p-value of less than 5%. And by the same token, a test statistic to the left of negative 1.96 would give us a p-value of less than 5% as well. And again, because for a two-sided test, the p-value is that shaded region in both tails. So and let me go back again. The test statistics that give a p-value of less than 5% would be test statistics that are either bigger than 1.96 or less than negative 1.96. And remember, if you have a p-value less than 5%, you're going to reject at the alpha equal 5% significance level. So these are precisely the test statistics that would make us reject the null hypothesis. Now the question is, what values of mu0 would give us test statistics like that? And you can just work through that by thinking about what we know the test statistic is. The test statistic is our x bar minus the mu value from the null hypothesis, which again is mu0, divided by the standard deviation of x bar, which is 1.5. And we're going to reject if this z test statistic is greater than 1.96. Well, you can just solve this little inequality for mu0, and you find that that test statistic is going to be bigger than 1.96 when mu0 is less than 100.76. Now that value 100.76 may be ringing a bell in your mind. It should, because that was the lower bound of the confidence interval, the 95% confidence interval that we calculated a few slides back. Similarly, you can show that the z-scores that are going to wind up less than minus 1.96 are going to correspond to mu zero values that are bigger than 106.64. And that is also familiar. That's the upper bound of that 95% confidence interval that we found earlier. So in other words, we're going to wind up rejecting the null hypothesis that mu equals some value mu zero in favor of the two-sided alternative at the 5% significance level if and only if that value in the null hypothesis falls outside the 95% confidence interval right here. That is a very interesting and informative result because it's relating the kind of values you'd reject in a significance test to the values that fall outside a confidence interval. So let's take a look at some examples here, for instance, right? Let's keep in mind our 95% confidence interval, which is here. And let's look at three different tests. And in fact, these are the ones we had discussed earlier. First of all, the null hypothesis that mu equals 100 versus the two-sided alternative. And secondly, the null hypothesis that mu equals 105 versus the two-sided alternative. And thirdly, the null hypothesis that mu equals 120 versus the two-sided alternative. What would these tests wind up saying? Well, if we keep in mind what we just said, that is, we reject the null if and only if that null value falls outside of our confidence interval, you can see that we're going to wind up rejecting the null hypothesis in this first test of mu equal 100 because 100 is not in this confidence interval. So if we actually did a significance test of this, went through and computed the p-value, we would find the p-value would be actually less than 5%, and so we would reject. But you can see that, given our discussion today, just from the confidence interval itself. 100 is outside the 95% confidence interval, so the p-value of this test is going to be less than 5%, and we'll wind up rejecting. What about the null hypothesis that mu is 105? Well, 105 is in the confidence interval here. So we're going to wind up not rejecting the null hypothesis here. And so that's we don't have to, in other words, go through the computation of the p-value in here. We can see that just from the confidence interval. For mu equal 120, we would say, well, is 120 in this confidence interval? The answer is no, and so we would wind up rejecting the null hypothesis that mu is 120. So of these three tests, just by looking at the null values and seeing if they're in the 95% confidence interval, we can determine how the test is going to turn out. That is, again, just repeating, for mu equal 100, we're going to reject the null because it's not in the confidence interval. For mu equal 105, we're going to fail to reject the null because it is in the confidence interval. And for mu equal 120, we're going to again reject the null hypothesis because it's not in the confidence interval. So the general principle here is this, that if you've got a level C confidence interval for a mean mu, and then you do a two-sided test of mu equal some value versus mu not equal to that value at the alpha equals 1 minus C significance level. So for instance, if C is 95, alpha would be 5. If C were 10%, alpha would be 90%, and so on. Then the null hypothesis will be rejected if and only if that null value in the null hypothesis falls outside the confidence interval. And the interpretation of this is really pretty straightforward. A level C confidence interval gives you the plausible values of mu with confidence level C based on the sample data. So what this discussion shows is that, at least for two-sided significance tests, you can really do the significance test in a snap as long as you have the corresponding confidence interval. So if I wanted to do, for instance, a significance test at the alpha equal 3% significance level, I could either just go through the procedure of computing a p-value, or I could calculate a 97% confidence interval, and that's because the alpha was 3%, and then see if the null value landed inside or outside that 97% confidence interval. If it's inside, we fail to reject the null. If it's outside, we reject the null. So in a sense, this shows that confidence intervals are more powerful than significance tests. If you've got a confidence interval in front of you, then at the right confidence level, then you can do your significance test just by seeing whether the null value is in the confidence interval or not. And remember here, the confidence level, like 95%, and the significance level have to add up to 100%. So this should help you with your homework for Friday night. Let me see if I can pull that up here. It's homework 31, relating CIs and tests. And it's just two problems, and especially the last one addresses directly this relationship between confidence intervals and significance tests. So I hope this little video has been helpful for you in that regard. Again, I know it's difficult doing math this way. Stick with it. Stay in touch. Let me know if you're having problems, and I'm sure we can find a way to work through them. And above all else, stay healthy. Y'all take care, and I'll be back in touch soon.